Okay, we're going to start talking about accelerated motion. Before we were doing constant or average speed. Now we're going to be changing speed up, slowing down, and so on. So the definition of acceleration is the rate of change of velocity. How fast your velocity is changing. Rate of change, whenever I want to calculate something that says rate, I'm going to divide by time. And so it's going to be acceleration. It's going to be change in velocity over the change in time. Now, it can be changed three ways, and all of these are considered acceleration in physics. We always say for acceleration, we tend to, in the English language, say that means speed's velocity. So something is speeding up, it's accelerating. But in physics, another way I can change velocity is I can slow it down. And that's still considered an acceleration. And the third way is a little bit subtle. Okay, remember, velocity is a vector, so if I change direction, I'm changing the velocity. So that's an acceleration too. Okay, right now we're talking about motion in one direction, so really just going to be doing the first two bullets. We will eventually get to change of direction. Now, which is it? The following examples is the object not accelerating. Drop ball from rest, it's going to speed up. Okay, so that's accelerating. Going at constant speed, so I'm not changing the speed in the same direction. That is going to be not accelerating. If we're going around a circular track, we are changing direction. So that is going to be an acceleration. And then this one, rolling to a stop, that means it slows down. So that is also going to be an acceleration. Okay, now, if we have constant acceleration, okay, in AP Physics 1 or Regents Physics, all the problems we dealt with acceleration were constant acceleration. And eventually, in AP Physics C, we'll be dealing with changing acceleration. But as long as it's constant acceleration, I can use any one of these equations. And the symbols in these equations are given here. A is acceleration, V0 is initial speed, and so on. The acceleration of gravity near the Earth's surface is G equals 9.8 meters per second downward. Okay? In class, we're almost always going to use minus 10, or 10 meters per second squared, downward for the acceleration of gravity. That makes the math a little bit easier, but remember, it's really 9.8. If we're going to work on a lag, we want to be really precise. Now, how to solve these types of problems? You may want to sketch a graph, or sketch a diagram. You don't have to, but sometimes it helps to visualize, especially for the more tricky problems. Part 2, you're going to write down your givens. Part 3, you're going to write your unknowns, what you're looking for. And then you're going to pick an equation and solve. Where people get in trouble with these is they pick the equation first, and then they try to stuff the stuff that's given in the problem into the equation, and they make a mistake. So, here's an example. The car is traveling at 20 meters per second, puts on the brakes, comes to a stop, while covering a distance of 80 meters. What is its acceleration? So, we're going to write down our givens. So, traveling at 20, that's the speed at the beginning of the problem. If we look back up here, initial speed is V0. So, V0 is 20 meters per second. Distance is 80 meters. Okay, so the numbers are obviously givens. Okay, there's another one in here that's a little bit subtle, comes to a stop. So at the end of the problem, its velocity is going to be 0 because it stopped. And then I'm looking for the acceleration. Now I can look at the equation up here, and I want the one that doesn't have timing. I have V0, delta x, and v. I'm looking for a. Time is not my list, so it turns out I'm going to use this equation right here. V squared equals V0 plus 2a delta x. So now I plug in, I get 0 equals 20 squared plus 2 times A. The distance was 80 meters. Solving this, I would 0 equals 400 minus 160A. If I solve that, I'll get an acceleration of minus 2.5. And the units for acceleration are meters per second squared. And what does that negative mean? We kind of get in the habit of when something's slowing down, the acceleration is negative. It's actually more the direction is what's happening. This car is moving in one way, and the acceleration of the push on it is the other way. And that's going to make it slow down. Second question. A stone is dropped from rest from a 30-meter high building. How long will it take to reach the ground below? So again, I want to write down my givens. I always have to have 3 givens in order to use one of these equations. The only obvious one is that delta x is 30 meters. Now, what else is in there? Well, it says it's dropped from rest. That means it's not moving at the beginning of the problem. So my v0 is going to be 0. And then the last thing is, since it's dropped, we're going to say that the acceleration of this thing is gravity. So it's going to be 10 meters per second squared. I didn't put the negative there, and I'm going to show you why in a minute in the next problem. And we're looking for how long, so I'm looking for time. So when I look at my equations, I want one with x, v0, a, and t in it. So I look up here. It turns out it's this long one right here, the delta x equation. So delta x is v0t plus 1/2 at squared. So then I can say 30 equals v0 is 0. So this whole part's going to be 0. No matter what my time is, 0 times the time is 0. So I don't have to worry about it. 1/2 times 10 times squared. If I do my algebra right with this, I'm going to end up with 6 is t squared. So t is going to be 2.45 seconds. Okay. Next problem. Ball is thrown upward with an initial speed of 30 along the Olympian air. So its starting speed is 30. Okay? It's not while it's in the person's hand. You might think the person's holding its speed is 0, but he's going to have to accelerate it upward until he lets go of it. Once he lets go of it, then gravity's going to pull it back down. So right at the moment he lets go, the initial velocity is going to be 30. Okay? And then this thing's going to go up and back down. Now, I know it's gravity that's going to pull it back down. But the gravity is 10 meters per second squared here. So now my givens are v0 is 30 meters per second. A is minus 10 meters per second squared. I wasn't careful with signs in problem 2. There was no change in direction. It was going down the whole time. So I didn't have to worry about it too much. Okay, in this case, though, I do have to. So 30 is going one way, and the acceleration is going the other way, so there's going to be a change in sign in there someplace. And I generally am going to make up positive and down negative. If I had been really careful in number 2, I'd have made the acceleration negative 10, okay? But I would have also made the delta x negative 30. Because delta x is displacement, where it is relative to the starting point. It's 30 below it, so minus 30. So anyway, going back to this problem, I have 2 givens now. I have to find a third one. Now, there's a very important point, okay, at the very top up here. At the very top, it's not going up and it's not going down. It's momentarily at rest. So v is 0 at the top. All right, and then I'm trying to find t, the time in the air. So now I have 3 givens and 1 unknown I can solve. If I look at my equations, the one I'm going to use for this one is going to be this one. V is v0 equals at. So v is v0 plus at. 0 equals 30 plus minus 10 t. When I settled out, t is 6 seconds. If I had the signs messed up there, what would have happened is I would have ended up with a negative 3 seconds per time, and that doesn't make any sense at all. Now, this is the time to the top, That's not what the question was asking me. It was asking for how long will be in the air altogether. And as long as there's no air friction, and for these problems, we're going to assume there's no air friction, because if there's air friction, the acceleration is no longer 10, it's no longer constant, and the problem becomes very, very, very difficult. In fact, the problem becomes unsolvable. So we're going to do it assuming there's no air friction. So the time up and the time down are going to be exactly the same. It's symmetrical. So the total time is going to be 6 seconds.